Okay, so for this question, we've got this cart that's rolling down, cart A, and then it's colliding with cart B, and then they stick together and they keep moving. So what we have, and you should be kind of looking at the question next to this video, the independent variable is the mass of cart B. So that's what we're changing, right? We're changing MB. MA is constant, and VA is constant. So our variables, right, our independent variable is the mass of cart B, and our dependent variable is their combined velocity that they move with after they strike each other. And our constants, our constant variables are MA and VA. And VA is held constant by just releasing this cart from the same height every time, right? So that's how we manage to hold VA constant. So the first thing this question says is to derive an equation relating MA, MB, VA, and VF. So if we use conservation of momentum just during the collision, right, so we can assume there's no external forces and we have a closed system during the collision. Obviously, it's not a closed system if we include the roll down the hill, because gravity causes the two-cart system to gain momentum, but there's momentum conserved during the collision itself. We could say something like MA VA is equal to the combined mass times VF, right? This is the initial momentum of the system, and then because they're both moving after the collision, this is the final momentum of the system. And then we have to, for part B, we're talking about the graph. So if we actually graph VF versus MB, what is it going to look like? So let's just kind of try it. So I think the best way to do this is to use our equation to help understand what's going on. So if we take the equation we just derived, VF is equal to, right, we solve for our our dependent variable over MA plus MB. And let's just think about what happens, right? So let's reason through it. So let's think about what this is going to equal. Let's say when MB equals 0. Let's think about what our equation is going to look like. All right, so when MB equals 0, our equation basically turns into right, this is 0. And then our equation becomes MAVA over MA. So these cancel out. And then VF basically just equals VA. So we should have, when MB equals 0, it should start right there at a certain value, VA, right? Right, so, and that makes sense, right? Because if MB is 0, when A hits B, it's not really going to slow down at all, right? Because there's no, right, there's like no extra momentum, or not extra momentum. The system's not gaining any mass during that collision, right? We basically have MAVA equals MAVF, so VA equals VF. Now let's think about what happens when MB is really, really big. All right, so when MB is really, really big, so we could maybe even write it like this, as MB goes to infinity, right? So when MB is really, really big, since it's in the denominator, right, as this gets really, really big, this will start to go to 0. And that makes sense too, right? Because if this is really, really huge compared to this, after they collide, they're going to move with almost no final velocity at all. So what we're going to see is that as B gets more and more massive, their combined speed after the collision is going to approach 0. So our graph should look something like that, with an intercept there. So right, that is Oh, geez. That is an intercept, a horizontal intercept. So that's what our graph is going to look like. Okay, and I might, yeah. No, I won't scratch those out of the solutions. So let's talk about part C now. Okay, C is asking, how should the students utilize LoggerPro to analyze their graph and obtain an experimental value for MA? Well, I think that's pretty straightforward. So the students should basically fit a function that is of the form y equals MA, what is it? We don't know MA, right? MA is our unknown thing. A times VA over A plus X. And then ask LoggerPro to calculate A for us. And then I would suggest whatever this is, like actually type in the number. Right, so then the computer would just basically be calculating this A value based on the graph that we made here. Okay, now for part D, it says we expect the momentum won't be perfectly conserved. Will this source of error cause the experimental value for MA to come out higher or lower than the actual value? So we expect that during this collision, the system's actually going to lose some momentum. And if the system loses momentum, then VF is lower than what it should be, right? So loss of the system's momentum lowers VF. And if we think about what that will look like, that will actually make it look like that A is less massive than it actually is, right? Because the system won't be moving as fast as it looks like it should, right? In other words, if VF comes out lower than it should be, it's going to look like MA is less than it should be. So will cause MA experimental value to be less than the MA actual value. Cool.